Our goal for today is to show that PDAs, well, really our goal for the next 2 days, is to show that PDAs and context-free grammars are equivalent. What we're going to do today is we're going to focus on this direction. We're going to show that a context-free grammar can be turned into a PDA. In other words, we're going to prove the theorem that for all G inside of context-free grammar, there exists a P inside of the PDAs where the language of the PDA is equal to the language of the grammar. Now, to do this, we're going to do a little bit of a circuitous route. We're going to first take context-free grammars, and we're going to turn them into a special variant of context-free grammars that are called a context-free grammar in Chomsky normal form. Chomsky normal form. And then those are the ones that we're going to turn into PDAs. So Noam Chomsky is a linguist from MIT who worked on a lot of the early aspects of this theory. And what Chomsky normal form is a way of simplifying context-free grammars. Now, what do I mean by simplifying them? Recall that the rules in a context-free grammar are the following. So rule is from the power set. It's a subset of the power set of the variables crossed with the variables union the terminals starred. Okay, so what does that mean? That means that we can have rules that say something like E goes to 5, or I'll do 6 instead. E goes to 6, or E goes to E plus E, or maybe I could have something that's like E goes to if E, then E, else E. Okay? Now, these rules are quite complicated, and you can kind of think of it by thinking about the parse trees that come out of them. In unrestrained context-free grammars, parse trees are arbitrary arity. In other words, I could have an E that was pointing to exactly one thing, let's say that's 6. Or I could have an E that was pointing to 2 things. Actually, in some sense, this E isn't really pointing to anything. Yeah, okay. It's pointing to the E, the plus, and the E. So it's pointing to that E and that E. Or I could have an E that's pointing to 3 things. There's the if part, the condition part, then there's the then branch, then there's the else branch. So notice that there are 0 variables here, 2 variables here, and 3 variables there. And so the number of variables on the right-hand side determines the arity of the parse tree. So the number of vars on right-hand side is the arity of the tree, of the parse tree node. And this can be complicated for analyzing context-free grammars because we have to consider every different possibility of how many things are going to be on the right-hand side. Because it's going to turn out that whenever we think about context-free grammars and we want to analyze them, we have to think about how many variables occur inside of it. And so what we would like to do is we would like to simplify this to a much tighter form. And so that's what Chomsky normal form does. So Chomsky normal form, or CNF, simplifies context-free grammars to ensure binary trees. So here's the way that it works. In Chomsky normal form, every rule is either 1, S goes to epsilon. That's one of the rules that you're allowed to have. 2, A goes to BC, where A is inside of V, and B and C are inside of V minus S. So notice that B and C are both variables, and they're not allowed to be S. You can never go back to S. Or rule 3, A goes to little a, where big A is inside of V, and little a is inside of sigma. So this right here is called the epsilon rule. So start is allowed to go to epsilon, and then a variable can either go to 2 variables or to a terminal. Now, of course, there could be many different different rules for the same left-hand sides. Now, here's the thing: every context or grammar can be converted into Chomsky normal form. Let's look at an example of that. So suppose that we have S goes to epsilon and S goes to 0, 1, S. Sorry, 0, S1. So this is the grammar for the 0 to the n, 1 to the n language. Now here is the process for doing that. Step one, add a new start state. A new start state. So what we'll do is we'll make it so our new start state will be called S prime, and it will go to the old start state S. Then we have the old rules, S goes to epsilon, and S goes to 0, S1. What did we just do by doing this? What we did is we ensured that the right-hand sides never mention S. Okay, good job. All right, now the next thing that we do is step 2. We remove any epsilon rules. So what does it mean to remove an epsilon rule? What it means is that we copy down all the rules except for ones that include epsilon. So we have S prime goes to S, and S goes to 0, S1. So we copied down all the rules that don't have an epsilon on the right-hand side. The next thing that we do is we look at all the rules that do have an epsilon. And if they have an epsilon, then we look at the left-hand side and we say, aha, S can be epsilon. So we go add extra rules, changing each S to be an epsilon. So there's a rule that says S prime goes to S, so we'll take that rule and we'll replace that S with an epsilon. Then we look at this rule and they say, aha, there's an S there, so we'll place that S with an epsilon. And these are new rules that we're adding. Now imagine that we had, and we don't have this one, but imagine we had something like X goes to AA, and A could be epsilon. Then what we would do is we would convert the left one to epsilon, the right one to epsilon, and them both. So we would have X goes to A, that's the left one being epsilon, the right one staying. X goes to A, that's the right one being epsilon, the left one staying. And then X goes to epsilon. Now, sometimes when we do this, we can get back a rule where there is another epsilon there. And I'll say remove any epsilon rules except start goes to epsilon. So we could do this and we could end up with another epsilon rule, in which case we'll do this again over and over and over again until we've removed all the epsilons except for the one that goes to the start state. Now the next thing that we do, step 3, okay, so step 0 is our original machine, Step 1 is we add a new start state. Step 3 is we remove what are called unit rules, which is when we have one variable going to another variable. And the way that we remove them is we just copy all the right-hand sides. So in this case, s prime going to s is an example of a unit rule. So we add s prime goes to 0 s1, because that's one of the things that s could be. We then also copy, and I'll do this as an or, the 0, 1, because that's something that s could be. So now we've removed this unit rule, and what we did is we just duplicated the things that were on the right-hand side of s. Now we still have that epsilon rule right there, and then we have s can go by itself to 0, s1, 0, 1. Okay, so here are our rules so far. Now the last thing that we do, step 4, is we add intermediate symbols. What an intermediate symbol is it's a symbol that stands in for a terminal. So we're going to add, let me see how much space I have. So we're going to add a rule that's called B is going to go to 1, and A is going to go to 0. So these are going to stand in for the terminal 0 and 1. Then what we're going to do is we're going to have a rule for X, and X is going to go to A, that's 0, and then S. Okay, so now we go and we use these in our old rules. So S prime, it's going to go to X, B, because it has to have a 0, an S, then a 1. So that's a 0, an S, and then a 1. Or it can go to AB, or it can go to epsilon. And then S can go to XB or AB. Now notice that what we've done is we've converted the grammar into Chomsky normal form. Every rule is either the start symbol going to epsilon, or a variable going to two other variables, or a variable going to a terminal. So now we have a greatly simplified version of a context-free grammar. Now, the reason that we want to do this is that now we can write programs that operate on context-free grammars, such as this program that will accept a context-free grammar and return a PDA and greatly simplify it. So let's do that now. So what we're going to do is we are going to compile a CFG in Chomsky normal form to a PDA. So that means that our input is Q, sigma, gamma, so no gamma. Q, sigma, sorry, I made a mistake. Our input is a context-free grammar, so that means it's V, sigma, R, which is a subset of the power set of V cross V union sigma star, and then we also have S, which is an element of V, where R inside of big R is either S epsilon, or A, B, C, or A little a. Now our output is going to be Q, sigma, gamma, Q0, delta, and F. All right, now let's talk about what each one of those pieces are. So here's the way that it's going to work. Q is going to be start, loop, and end, plus a state for every variable. Q0 is going to be start. Gamma is going to be V union sigma. Okay? F is going to just be end. So if we were to look at a picture of this, that means that our start state is start, and then we have an accepting state called end. Okay? And if we take an example of like this one, that means that we're going to have a state called S prime, S, X, A, and B. So we have states S prime, S, X, A, and B. And we also have the loop state. Right? This is what we have so far. Now all we need to do is describe delta. So here's the way that it works. Delta of start epsilon epsilon is equal to the set that contains the place where we're going, which is the start state, and we push on a $sign. Oh yeah, there's one more thing inside of gamma, which is $sign. You know what I'm going to do? I'm going to put this picture on the next page. And that way we can write it big. And let me just rearrange things a little bit here. Here's our output. And then move that up here. And I think we'll be good to go. And let me actually give some space right here. So we'll have all the rules listed like that. Okay. So let's make this much bigger now. So 14.6. Okay. So we have our start state. All right. And we have S prime over here. We have S. We have X. And we have A, B, and I'll put end over here. I'll put end over here in this corner. And that's going to be accepting. All right. So now the first thing that we add is we add a mapping from state to the start symbol that's labeled epsilon, epsilon, arrow, star. Okay, so that's the first step. Now the next thing that we do is we say that for all big A inside of V, delta of big A says epsilon, epsilon equals loop A. All right? So what that means is that we're going to have our loop state right here. Right? And there's going to be a rule that goes from there to there that says epsilon, epsilon, arrow, S prime. And there's a rule that says epsilon, epsilon, arrow, S, and epsilon, epsilon, arrow, X. And over here it says, actually, you know what? That's kind of annoying. Let's erase these ones and move them over to here. So we'll put A here and B here. Okay, so this one is going to say epsilon, epsilon, arrow, B, and this one will say epsilon, epsilon, arrow, A. So the idea here is that each one of these states, its job is to push on the appropriate symbol. Okay? So now, if we were to run this, we push on the $, then we push on the S prime, and now we're in the loop state. So now all the action is going to happen in the loop state. Whoops. There we go. Okay. So the next thing that we're going to do is we're going to consider each rule. So we'll say if S epsilon is inside of the rules, then delta of loop epsilon S will include if that's the case, then this will include what do I want to say? Then this will include loop epsilon. So what that means is that there's a rule right here that says that if we see epsilon on the input and S prime, then we can pop that off. Okay. The next rule, oh yeah, there's another thing that we want to say, which is that we want to say that delta of loop epsilon $, will always contain end epsilon. So that means that there's an arrow that goes from here to end. Let's put end over here actually. End. And this one says epsilon $ arrow epsilon. And let's erase this one. And let's move this all over a bit. Okay. All right. So now what's next? The next thing is that we're going to add rules of the following form. We're going to add rules that say for all little a inside of sigma, delta of loop, that thing in the input and that thing on the stack will include loop epsilon. So that means that we also have a rule that says 0, 0 goes to epsilon, and 1, 1 goes to epsilon. Because those are the only things in our input, or that are in sigma. Okay. Now, we also need to consider other rules. We say, if A is inside of R, then delta of loop epsilon, big A, on the stack will include loop little a. So that means that if we look at our rule, so there's a rule that says that A goes to 0 and B goes to 1. So that means that if we see epsilon in the input, an A on the stack, then we can push on a 0. If we see an epsilon and a B, then we can push on a 1. Right? So now what's next? So then the last thing that we do is we say that if A, B, C is inside of the rules, then delta of loop epsilon A will include, we're going to go to the B state after pushing C. So what does this mean? So here are the rules that this applies to. Let's copy and paste them for convenience. copy them, come over here and paste them. Let's move them down here. Actually, let's move them there is probably a good spot. Okay. So now what that means is that the loop is going to have 3 ways to get to the A state. So we're going to go down here, and we're going to go over to the X state, and we're going to go down and go over to the A state. Ooh, it's kind of annoying the way that I did this. Let's erase that and give ourselves some more space. Okay, so on these labels, the ones that go to the X state, oh yeah, we also need one for the S state. Ooh, yeah, this is really annoying. Okay, where can I fit this? I've got an idea. Okay. Graph drawing is hard. All right, we'll give ourselves a lot of space right there. Okay. So the first thing, let's look at the ones that go to A. So we're going from loop to A. Well, that's this rule, and oh yeah, we actually don't need one for S. So that's these rules, because these rules end in A. So what these ones do is they say, if we see epsilon on the input, and we see an S prime in the stack, so that's for S prime going to A, that means that we push a B. Next, if we see an epsilon and an S, then we push a B and we go to A. All right, so those, and then there's a last one that says if we see epsilon on the input, X on the stack, then we push on an S. So we push on a B and go to A, we push on a B and go to A, we push on an S and go to A. And what that's going to do is it's going to push on an A. Now this ones that go to X, what those are going to do is they're going to say if we see an epsilon and an S prime, then we push on a B. Or if we see an epsilon and an S, then we push on a B. And this is the entire machine. Now you may say to yourself, how could this possibly work? Is this real? Well, what I'm going to do is I'm going to slide my page up, and I'm going to be looking at this while we write out what it does. Actually, maybe what I'll do is I'll try to keep as much in as possible. Okay. So imagine that we see, so we start with epsilon on the stack, and then we're in the start state. And let's suppose that our input is 0, 0, 1, 1. Well, the first thing that we do is we push on a $, and we go to the S prime state. And we have 0, 0, 1, 1. Well, the S prime state, what it does is it pushes on an S prime. So we have $, S prime, and now we're in the loop state, which I'll just write as L, so it takes up less space. Then we have 0, 0, 1, 1. Now we're in the loop state right here, and we see that the top of the stack contains an S prime. Let's look at all of the rules. So S prime could go to epsilon. 0 is in the input, but there's no 0 on the stack. There's no A on the top of the stack. There's no B on the top of the stack. There is an S prime that goes to a B, and there is, yeah. So basically, we can follow this rule where the S prime goes to epsilon, or this one where it goes to B. Let's follow that one. So what we'll do there is we'll pop off the S prime and push on a B, and then this goes to the X state, and then we have 0, 0, 1, 1. Okay? Well, now we're in the X state, so that means that we're going to go back to the loop state after pushing on an X. So we're in the loop state, and we see 0, 0, 1, 1. Well, now we're in the loop state, and there's an x there. So if there's an x, that means that the only rule that can be followed is this one right here. So that one, what it does is it pushes on. So we have b, because we have the $b, and then that x has been replaced with s. And then we are now in the a state, and we have 0, 0, 1, 1. Well, the a state, what it does is it pushes on an a and brings us to the loop state. Well, there's an a there, so the only rule that could possibly apply is this one, so we're going to push on a 0. So we go back to the loop state, and there's a 0 there, L 0, 0, 1, 1. Well, now there's a 0 in the input and a 0 in the stack, and so that means that this is the only rule that applies. So in that case, we're going to go to $BS L 0, 1, 1. Something really cool and important just happened. What we did is we read the first character from our input. And the way that we read that first character from the input is that notice that the stack, what it has is it sort of has like a mirror of what the string is going to be. And once we non-deterministically generated part of that, we then checked one character and made sure that we were right on the right track. All right, so we're in the L state. There's an S there. So in this case, we're going to choose this transition to X. So we're going to go $. Actually, no, we're not going to do that one. We're not going to go to X. We're going to go to A. So we're going to follow this rule. So we're going to see the B is going to stay there. We're going to pop off the S and replace it with a B. And then we're going to go to the A state, and we have a 0, 1, 1 in front of us. Now, because we're in the A state, then we're going to push on that A and go to the L state with a 0, 1, 1 in front of us. Then we see an A, and we're going to turn that into a 0. So we do $BB0 L 0, 1, 1. Then we're going to pop that off, so then we get $BB L 1, 1. Then we're going to see $B1 L 1, 1. That goes to $B L1. Then we get $1 L1. Then we get $L epsilon. Then we get epsilon and epsilon, and then we get a yes. So the way that this transformation works, where we can turn the context-free grammar into a PDA, is that we have this schematic where we always have these three states, start, loop, and end, and they all cooperate with one another to make it so that the stack basically simulates the derivation of the string which is given in the input. And then we are constantly checking to make sure that that string is the correct one. I think that this is really cool and beautiful. It's kind of amazing that people thought of this, and it's so simple. We can turn any context-free grammar, no matter how complicated. First, we turn it into Chomsky normal form, and then once it's in Chomsky normal form, we turn it into a PDA that has as many states as there are variables plus 3. And we have these very simple rules for determining exactly what those states are. Well, that's it for now. Next time we'll talk about going in the other direction and turning PDAs into context-free grammars.